Bromine. Bromine is a chemical element with symbol Br and atomic number 35. It is the third lightest halogen, and is a fuming red-brown liquid at room temperature that evaporates readily to form a similarly colored gas. Its properties are thus intermediate between those of chlorine and iodine. Isolated independently by two chemists, Jacob Löwig and Antoine Jérôme Balard, its name was derived from the ancient Greek beta-rho-mu-omicron, referencing its sharp and disagreeable smell. Elemental bromine is very reactive and thus does not occur free in nature, but in colorless soluble crystalline mineral halide salts, analogous to table salt. While it is rather rare in the Earth's crust, the high solubility of the bromide ion has caused its accumulation in the oceans. Commercially, the element is easily extracted from brine pools, mostly in the United States, Israel, and China. The mass of bromine in the oceans is about 1/300th that of chlorine. At high temperatures, organobromine compounds readily dissociate to yield free bromine atoms, a process that stops free radical chemical chain reactions. This effect makes organobromine compounds useful as fire retardants, and more than half the bromine produced worldwide each year is put to this purpose. The same property causes ultraviolet sunlight to dissociate volatile organobromine compounds in the atmosphere to yield free bromine atoms, causing ozone depletion. As a result, many organobromide compounds such as the pesticide methyl bromide are no longer used. Bromine compounds are still used in well drilling fluids, in photographic film, and as an intermediate in the manufacture of organic chemicals. Large amounts of bromide salts are toxic from the action of soluble bromide ion, causing bromism. However, a clear biological role for bromide ion and hypobromic acid has recently been elucidated, and it now appears that bromine is an essential trace element in humans. The role of biological organobromine compounds in sea life such as algae has been known for much longer. As a pharmaceutical, the simple bromide ion has inhibitory effects on the central nervous system, and bromide salts were once a major medical sedative, before replacement by shorter-acting drugs. They retain niche uses as antiepileptics. Bromine was discovered independently by two chemists, Jacob Löwig and Antoine Balard, in 1825 and 1826, respectively. Löwig isolated bromine from a mineral water spring from his hometown Bad Kreuznach in 1825. Löwig used a solution of the mineral salt saturated with chlorine and extracted the bromine with diethyl ether. After evaporation of the ether, a brown liquid remained. With this liquid as a sample of his work, he applied for a position in the laboratory of Leopold Gmelin in Heidelberg. The publication of the results was delayed and Balard published his results first. Balard found bromine chemicals in the ash of seaweed from the salt marshes of Montpellier. The seaweed was used to produce iodine, but also contained bromine. Balard distilled the bromine from a solution of seaweed ash saturated with chlorine. The properties of the resulting substance were intermediate between those of chlorine and iodine, thus he tried to prove that the substance was iodine monochloride, but after failing to do so he was sure that he had found a new element, and named it muride, derived from the Latin word muria for brine. After the French chemists Louis-Nicolas Vauquelin, Louis-Jacques Thénard, and Joseph-Louis Gay-Lussac approved the experiments of the young pharmacist Balard, the results were presented at a lecture of the Académie des Sciences and published in Annales de Chimie et Physique. In his publication, Balard states that he changed the name from muride to brome on the proposal of M. Anglada. Brome derives from the Greek beta-rho-omega-mu-omicron. Other sources claim that the French chemist and physicist Joseph-Louis Gay-Lussac suggested the name brome for the characteristic smell of the vapors. Bromine was not produced in large quantities until 1858, when the discovery of salt deposits in Stassfurt enabled its production as a byproduct of potash. Apart from some minor medical applications, the first commercial use was the daguerreotype. In 1840, bromine was discovered to have some advantages over the previously used iodine vapor to create the light-sensitive silver halide layer in daguerreotype. Potassium bromide and sodium bromide were used as anticonvulsants and sedatives in the late 19th and early 20th centuries, but were gradually superseded by chloral hydrate and then by the barbiturates. In the early years of the First World War, bromine compounds such as XYLYL bromide were used as poison gas. Bromine is the third halogen, being a nonmetal in group 17 of the periodic table. Its properties are thus similar to those of fluorine, chlorine, and iodine, and tend to be intermediate between those of the two neighboring halogens, chlorine and iodine. Bromine has the electron configuration 3d104s24p5, with the 7 electrons in the fourth and outermost shell acting as its valence electrons. Like all halogens, it is thus 1 electron short of a full octet, and is hence a strong oxidizing agent, reacting with many elements in order to complete its outer shell. Corresponding to periodic trends, it is intermediate in electronegativity between chlorine and iodine, and is less reactive than chlorine and more reactive than iodine. It is also a weaker oxidizing agent than chlorine, but a stronger one than iodine. Conversely, the bromide ion is a weaker reducing agent than iodide, but a stronger one than chloride. These similarities led to chlorine, bromine, and iodine together being classified as one of the original triads of Johann Wolfgang Dobereiner, whose work foreshadowed the periodic law for chemical elements. It is intermediate in atomic radius between chlorine and iodine, and this leads to many of its atomic properties being similarly intermediate in value between chlorine and iodine, such as first ionization energy, electron affinity, enthalpy of dissociation of the X2 molecule, ionic radius, and XX bond length. The volatility of bromine accentuates its very penetrating, choking, and unpleasant odor. All 4 stable halogens experience intermolecular van der Waals forces of attraction, and their strength increases together with number of electrons among all homonuclear diatomic halogen molecules. Thus, the melting and boiling points of bromine are intermediate between those of chlorine and iodine. As a result of the increasing molecular weight of the halogens down the group, the density and heats of fusion and vaporization of bromine are again intermediate between those of chlorine and iodine, although all their heats of vaporization are fairly low thanks to their diatomic molecular structure. The halogens darken in color as the group is descended. Fluorine is a very pale yellow gas, chlorine is greenish yellow, and bromine is a reddish-brown volatile liquid that melts at 7.2 degrees C and boils at 58.8 degrees C. This trend occurs because the wavelengths of visible light absorbed by the halogens increase down the group. Specifically, the color of a halogen, such as bromine, results from the electron transition between the highest occupied antibonding πg molecular orbital and the lowest vacant antibonding sigma u molecular orbital. The color fades at low temperatures, so that solid bromine at 195 degrees C is pale yellow. Like solid chlorine and iodine, solid bromine crystallizes in the orthorhombic crystal system, in a layered lattice of Br2 molecules. The Br-Br distance is 227 pm and the Br-Br distance between molecules is 331 pm within a layer and 399 pm between layers. This structure means that bromine is a very poor conductor of electricity, with a conductivity of around 5 × 1013 ω1 cm1 just below the melting point, although this is better than the essentially undetectable conductivity of chlorine. At a pressure of 55 GPa, bromine undergoes an insulator-to-metal transition. At 75 GPa it changes to a face-centered orthorhombic structure. At 100 GPa it changes to a body-centered orthorhombic monatomic form. Bromine has 2 stable isotopes, 79Br and 81Br. These are its only 2 natural isotopes, with 79Br making up 51% of natural bromine and 81Br making up the remaining 49%. Both have nuclear spin 3/2 and thus may be used for nuclear magnetic resonance, although 81Br is more favorable. The relatively 1:1 distribution of the 2 isotopes in nature is helpful in identification of bromine-containing compounds using mass spectroscopy. Other bromine isotopes are all radioactive, with half-lives too short to occur in nature. Of these, the most important are 80Br, 80MBr, and 82Br, which may be produced from the neutron activation of natural bromine. The most stable bromine radioisotope is 77Br. The primary decay mode of isotopes lighter than 79Br is electron capture to isotopes of selenium. That of isotopes heavier than 81Br is beta decay to isotopes of krypton, and 80Br may decay by either mode to stable 80Se or 80Kr. Bromine is intermediate in reactivity between chlorine and iodine, and is one of the most reactive elements. Bond energies to bromine tend to be lower than those to chlorine but higher than those to iodine, and bromine is a weaker oxidizing agent than chlorine but a stronger one than iodine. This can be seen from the standard electrode potentials of the X2/X couples. Bromination often leads to higher oxidation states than iodination but lower or equal oxidation states to chlorination. Bromine tends to react with compounds including MM, MH, or MC bonds to form MBr bonds. The simplest compound of bromine is hydrogen bromide, HBr. It is mainly used in the production of inorganic bromides and alkyl bromides, and as a catalyst for many reactions in organic chemistry. Industrially, it is mainly produced by the reaction of hydrogen gas with bromine gas at 200–400 degrees C with a platinum catalyst. However, reduction of bromine with red phosphorus is a more practical way to produce hydrogen bromide in the laboratory. At room temperature, hydrogen bromide is a colorless gas, like all the hydrogen halides apart from hydrogen fluoride, since hydrogen cannot form strong hydrogen bonds to the large and only mildly electronegative bromine atom. However, weak hydrogen bonding is present in solid crystalline hydrogen bromide at low temperatures, similar to the hydrogen fluoride structure, before disorder begins to prevail as the temperature is raised. Aqueous hydrogen bromide is known as hydrobromic acid, which is a strong acid because the hydrogen bonds to bromine are too weak to inhibit dissociation. The HBr/H2O system also involves many hydrates HBr and H2O for N equals 1, 2, 3, 4, and 6, which are essentially salts of bromine anions and hydronium cations. Hydrobromic acid forms an azeotrope with boiling point 124.3 degrees C at 47.63 GHBr per 100 G solution, thus hydrobromic acid cannot be concentrated beyond this point by distillation. Unlike hydrogen fluoride, anhydrous liquid hydrogen bromide is difficult to work with as a solvent, because its boiling point is low, it has a small liquid range, its dielectric constant is low and it does not dissociate appreciably into H2Br and HBr2 ions. The latter, in any case, are much less stable than the bifluoride ions due to the very weak hydrogen bonding between hydrogen and bromine, though its salts with very large and weakly polarizing cations such as Cs and Nr+4 may still be isolated. Anhydrous hydrogen bromide is a poor solvent, only able to dissolve small molecular compounds such as nitrosyl chloride and phenol, or salts with very low lattice energies such as tetralkylammonium halides. Nearly all elements in the periodic table form binary bromides. The exceptions are decidedly in the minority and stem in each case from one of three causes: extreme inertness and reluctance to participate in chemical reactions, extreme nuclear instability hampering chemical investigation before decay and transmutation, and having an electronegativity higher than bromines, so that the resultant binary compounds are formally not bromides but rather oxides, nitrides, fluorides, or chlorides of bromine. Bromination of metals with Br2 tends to yield lower oxidation states than chlorination with Cl2 when a variety of oxidation states is available. Bromides can be made by reaction of an element or its oxide, hydroxide, or carbonate with hydrobromic acid, and then dehydrated by mildly high temperatures combined with either low pressure or anhydrous hydrogen bromide gas. These methods work best when the bromide product is stable to hydrolysis. Otherwise, the possibilities include high-temperature oxidative bromination of the element with bromine or hydrogen bromide, high-temperature bromination of a metal oxide or other halide by bromine, a volatile metal bromide, carbon tetrabromide, or an organic bromide. For example, niobium oxide reacts with carbon tetrabromide at 370 degrees C to form niobium bromide. Another method is halogen exchange in the presence of excess halogenating reagent, for example. When a lower bromide is wanted, either a higher halide may be reduced using hydrogen or a metal as a reducing agent, or thermal decomposition or disproportionation may be used, as follows. Most of the bromides of the pre-transition metals are mostly ionic, while nonmetals tend to form covalent molecular bromides, as do metals in high oxidation states from +3 and above. Silver bromide is very insoluble in water and is thus often used as a qualitative test for bromine. The halogens form many binary, diamagnetic interhalogen compounds with stoichiometries XY, XY3, XY5, and XY7, and bromine is no exception. Bromine forms a monofluoride and monochloride, as well as a trifluoride and pentafluoride. Some cationic and anionic derivatives are also characterized, such as BRF2, BRCl2, BRF+2, BRF+4, and BRF+6. Apart from these, some pseudohalides are also known, such as cyanogen bromide, bromine thiocyanate, and bromine azide. The pale brown bromine monofluoride is unstable at room temperature, disproportionating quickly and irreversibly into bromine, bromine trifluoride, and bromine pentafluoride. It thus cannot be obtained pure. It may be synthesized by the direct reaction of the elements, or by the comproportionation of bromine and bromine trifluoride at high temperatures. Bromine monochloride, a red-brown gas, quite readily dissociates reversibly into bromine and chlorine at room temperature and thus also cannot be obtained pure, though it can be made by the reversible direct reaction of its elements in the gas phase or in carbon tetrachloride. Bromine monofluoride in ethanol readily leads to the monobromination of the aromatic compounds PHX. This is due to heterolytic fission of the Br-F bond, leading to rapid electrophilic bromination by Br+. At room temperature, bromine trifluoride is a straw-colored liquid. It may be formed by directly fluorinating bromine at room temperature and is purified through distillation. It reacts explosively with water and hydrocarbons, but is a less violent fluorinating reagent than chlorine trifluoride. It reacts vigorously with boron, carbon, silicon, arsenic, antimony, iodine, and sulfur to give fluorides, and also reacts with most metals and their oxides. As such, it is used to oxidize uranium to uranium hexafluoride in the nuclear industry. Refractory oxides tend to be only partially fluorinated, but here the derivatives KBrF4 and BrF2SBF6 remain reactive. Bromine trifluoride is a useful non-aqueous ionizing solvent, since it readily dissociates to form BrF+2 and BrF4 and thus conducts electricity. Bromine pentafluoride was first synthesized in 1930. It is produced on a large scale by direct reaction of bromine with excess fluorine at temperatures higher than 150 degrees C, and on a small scale by the fluorination of potassium bromide at 25 degrees C. It is a very vigorous fluorinating agent, although chlorine trifluoride is still more violent. Bromine pentafluoride explodes on reaction with water and fluorinates silicates at 450 degrees C. Although dibromine is a strong oxidizing agent with a high first ionization energy, very strong oxidizers such as peroxidisulfuryl fluoride can oxidize it to form the cherry red Br+2 cation. A few other bromine cations are known, namely the brown Br+3 and dark brown Br+5. The tribromide anion, Br3, has also been characterized. It is analogous to triiodide. Bromine oxides are not as well characterized as chlorine oxides or iodine oxides, as they are all fairly unstable. It was once thought that they could not exist at all. Bromine monoxide is a dark brown solid which, while reasonably stable at 60 degrees C, decomposes at its melting point of 17.5 degrees C. It is useful in bromination reactions and may be made from the low-temperature decomposition of bromine dioxide in a vacuum. It oxidizes iodine to iodine pentoxide and benzene to 1,4-benzoquinone. In alkaline solutions, it gives the hypobromite anion. So-called bromine dioxide, a pale yellow crystalline solid, may be better formulated as bromine perbromate, Bro3. It is thermally unstable above 40 degrees C, violently decomposing to its elements at 0 degrees C. Bromine trioxide, Sin-Bro2, is also known. It is the anhydride of hypobromic acid and bromic acid. It is an orange crystalline solid which decomposes above 40 degrees C, if heated too rapidly, it explodes around 0 degrees C. A few other unstable radical oxides are also known, as are some poorly characterized oxides, such as dibromine pentoxide, tribromine octoxide, and bromine trioxide. The 4 oxoacids, hypobromic acid, bromic acid, and perbromic acid, are better studied due to their greater stability, though they are only so in aqueous solution. When bromine dissolves in aqueous solution, the following reactions occur. Hypobromic acid is unstable to disproportionation. The hypobromite ions thus formed disproportionate readily to give bromide and bromate. Bromic acids and bromides are very unstable, although the strontium and barium bromides are known. More important are the bromates, which are prepared on a small scale by oxidation of bromide by aqueous hypochlorite, and are strong oxidizing agents. Unlike chlorates, which very slowly disproportionate to chloride and perchlorate, the bromate anion is stable to disproportionation in both acidic and aqueous solutions. Bromic acid is a strong acid. Bromides and bromates may come proportionate to bromine as follows. There were many failed attempts to obtain perbromates and perbromic acid, leading to some rationalizations as to why they should not exist, until 1968 when the anion was first synthesized from the radioactive beta decay of unstable 83CO24. Today, perbromates are produced by the oxidation of alkaline bromate solutions by fluorine gas. Excess bromate and fluoride are precipitated as silver bromate and calcium fluoride, and the perbromic acid solution may be purified. The perbromate ion is fairly inert at room temperature but is thermodynamically extremely oxidizing, with extremely strong oxidizing agents needed to produce it, such as fluorine or xenon difluoride. The BRO bond in Bro4 is fairly weak, which corresponds to the general reluctance of the 4p elements to attain their maximum possible oxidation state, as they come after the scandide contraction characterized by the pore shielding afforded by the radial nodeless 3d orbitals. Like the other carbon-halogen bonds, the Cbr bond is a common functional group that forms part of core organic chemistry. Formally, compounds with this functional group may be considered organic derivatives of the bromide anion. Due to the difference of electronegativity between bromine and carbon, the carbon in a Cbr bond is electron deficient and thus electrophilic. The reactivity of organobromine compounds resembles but is intermediate between the reactivity of organochlorine and organoiodine compounds. For many applications, organobromides represent a compromise of reactivity and cost. Organobromides are typically produced by additive or substitutive bromination of other organic precursors. Bromine itself can be used, but due to its toxicity and volatility safer brominating reagents are normally used, such as N-bromosuccinamide. The principal reactions for organobromides include dehydrobromination, Grignard reactions, reductive coupling, and nucleophilic substitution. Organobromides are the most common organohalides in nature, even though the concentration of bromide is only 0.3% of that for chloride in seawater, because of the easy oxidation of bromide to the equivalent of Br+, a potent electrophile. The enzyme bromoperoxidase catalyzes this reaction. The oceans are estimated to release 1-2 million tons of bromoform and 56,000 tons of bromomethane annually. An old qualitative test for the presence of the alkene functional group is that alkenes turn brown aqueous bromine solutions colorless, forming a bromohydrin with some of the dibromolcane also produced. The reaction passes through a short-lived strongly electrophilic bromonium intermediate. This is an example of a halogen addition reaction. Bromine is significantly less abundant in the crust than fluorine or chlorine, comprising only 2.5 parts per million of the Earth's crustal rocks, and then only as bromide salts. It is the 46th most abundant element in Earth's crust. It is significantly more abundant in the oceans, resulting from long-term leaching. There, it makes up 65 parts per million, corresponding to a ratio of about 1 bromine atom for every 660 chlorine atoms. Salt lakes and brine wells may have higher bromine concentrations. For example, the Dead Sea contains 0.4% bromide ions. It is from these sources that bromine extraction is mostly economically feasible. The main sources of bromine are in the United States and Israel. The element is liberated by halogen exchange, using chlorine gas to oxidize Br to Br2. This is then removed with a blast of steam or air, and is then condensed and purified. Today, bromine is transported in large capacity metal drums or lead-lined tanks that can hold hundreds of kilograms or even tons of bromine. The bromine industry is about 1/100th the size of the chlorine industry. Laboratory production is unnecessary because bromine is commercially available and has a long shelf life. A wide variety of organobromine compounds are used in industry. Some are prepared from bromine and others are prepared from hydrogen bromide, which is obtained by burning hydrogen in bromine. Brominated flame retardants represent a commodity of growing importance, and make up the largest commercial use of bromine. When the brominated material burns, the flame retardant produces hydrobromic acid, which interferes in the radical chain reaction of the oxidation reaction of the fire. The mechanism is that the highly reactive hydrogen radicals, oxygen radicals, and hydroxy radicals react with hydrobromic acid to form less reactive bromine radicals. Bromine atoms may also react directly with other radicals to help terminate the free radical chain reactions that characterize combustion. To make brominated polymers and plastics, bromine-containing compounds can be incorporated into the polymer during polymerization. One method is to include a relatively small amount of brominated monomer during the polymerization process. For example, vinyl bromide can be used in the production of polyethylene, polyvinyl chloride, or polypropylene. Specific highly brominated molecules can also be added that participate in the polymerization process. For example, tetrabromobisphenol A can be added to polyesters or epoxy resins, where it becomes part of the polymer. Epoxies used in printed circuit boards are normally made from such flame retardant resins, indicated by the FR in the abbreviation of the products. In some cases, the bromine-containing compound may be added after polymerization. For example, decabromodafinil ether can be added to the final polymers. A number of gaseous or highly volatile brominated halomethane compounds are non-toxic and make superior fire suppressant agents by this same mechanism, and are particularly effective in enclosed spaces such as submarines, airplanes, and spacecraft. However, they are expensive and their production and use has been greatly curtailed due to their effect as ozone-depleting agents. They are no longer used in routine fire extinguishers, but retain niche uses in aerospace and military automatic fire suppression applications. They include bromochloromethane, bromochlorodifluoromethane, and bromotrifluoromethane. Silver bromide is used, either alone or in combination with silver chloride and silver iodide, as the light-sensitive constituent of photographic emulsions. Ethylene bromide was an additive in gasolines containing lead anti-engine knocking agents. It scavenges lead by forming volatile lead bromide, which is exhausted from the engine. This application accounted for 77% of the bromine use in 1966 in the US. This application has declined since the 1970s due to environmental regulations. Poisonous bromomethane was widely used as pesticide to fumigate soil and to fumigate housing, by the tenting method. Ethylene bromide was similarly used. These volatile organobromine compounds are all now regulated as ozone depletion agents. The Montreal Protocol on substances that deplete the ozone layer scheduled the phase-out for the ozone-depleting chemical by 2005, and organobromide pesticides are no longer used. Before the Montreal Protocol in 1991, an estimated 35,000 tons of the chemical were used to control nematodes, fungi, weeds, and other soil-borne diseases. In pharmacology, inorganic bromide compounds, especially potassium bromide, were frequently used as general sedatives in the 19th and early 20th century. Bromides in the form of simple salts are still used as anticonvulsants in both veterinary and human medicine, although the latter use varies from country to country. For example, the U.S. Food and Drug Administration does not approve bromide for the treatment of any disease, and it was removed from over-the-counter sedative products like Bromo Seltzer, in 1975. Commercially available organobromine pharmaceuticals include the vasodilator nicergolin, the sedative brodazolam, the anti-cancer agent pepobromin, and the antiseptic merbromin. Otherwise, organobromine compounds are rarely pharmaceutically useful, in contrast to the situation for organofluorine compounds. Several drugs are produced as the bromide salts, but in such cases bromide serves as an innocuous counterion of no biological significance. Other uses of organobromine compounds include high-density drilling fluids, dyes, and pharmaceuticals. Bromine itself, as well as some of its compounds, are used in water treatment, and is the precursor of a variety of inorganic compounds with an enormous number of applications. Zinc-bromine batteries are hybrid flow batteries used for stationary electrical power backup and storage, from household scale to industrial scale. A 2014 study suggests that bromine is a necessary cofactor in the biosynthesis of collagen-4, making the element essential to basement membrane architecture and tissue development in animals. Nevertheless, no clear deprivation symptoms or syndromes have been documented. In other biological functions, bromine may be non-essential but still beneficial when it takes the place of chlorine. For example, in the presence of hydrogen peroxide, H2O2, formed by the eosinophil, and either chloride or bromide ions, eosinophil peroxidase provides a potent mechanism by which eosinophils kill multicellular parasites and some bacteria. Eosinophil peroxidase is a haloperoxidase that preferentially uses bromide over chloride for this purpose, generating hypobromite, although the use of chloride is possible. Although alpha haloesters are generally thought of as highly reactive, and therefore, toxic intermediates in organic synthesis, mammals, including humans, cats, and rats, appear to biosynthesize traces of an alpha bromoester, 2-octyl-4-bromo-3-oxybutanoate, which is found in their cerebrospinal fluid and appears to play a yet unclarified role in inducing REM sleep. Human neutrophils use myeloperoxidase, H2O2, and Br to brominate deoxycytidine, which is a mutagen, so transhalogenation reactions with bromine may be responsible for some human cancers. Marine organisms are the main source of organobromine compounds, and it is in these organisms that the essentiality of bromine is on much firmer ground. More than 1,600 such organobromine compounds were identified by 1999. The most abundant is methyl bromide, of which an estimated 56,000 tons is produced by marine algae each year. The essential oil of the Hawaiian alga Asparagopsis taxiformis consists of 80% bromoform. Most of such organobromine compounds in the sea are made by the action of a unique algal enzyme, vanadium bromoperoxidase. The bromide anion is not very toxic, a normal daily intake is 2 to 8 mg. However, high levels of bromide chronically impair the membrane of neurons, which progressively impairs neuronal transmission, leading to toxicity, known as bromism. Bromide has an elimination half-life of 9 to 12 days, which can lead to excessive accumulation. Doses of 0.5 to 1 gram per day of bromide can lead to bromism. Historically, the therapeutic dose of bromide is about 3 to 5 grams of bromide, thus explaining why chronic toxicity was once so common. While significant and sometimes serious disturbances occur to neurologic, psychiatric, dermatological, and gastrointestinal functions, death from bromism is rare. Bromism is caused by a neurotoxic effect on the brain which are